All right, now that you're getting into your experiments, I'm sure you're getting a good sense for how messy and noisy biological data can really be. So let's talk a little bit about how experimental biologists handle this. All right, so let's just take a really simple example. Let's say we're interested in figuring out if Emory students are taller than Georgia Tech students. What kind of error in this experiment will we likely encounter? So one type of error is biological error, and that's variation that's just inherent to your biological system, right? So if you take a population of people, they will not all be the same height. There's going to be variation there. The main way that biologists generally handle this is to, instead of collecting, measuring one Emory student and one Georgia Tech students, we would take replicate data. So we would measure many Emory students and many Georgia Tech students. Okay, the other type of experimental error is technical error, and that is error associated with your experimental procedure, and you want to try to minimize this error as much as possible. So in our example here, we could have inconsistent measuring technique, right? So we need to make sure that we would normalize either everybody takes their shoes off before we measure their height or nobody does, right? We need to make your measurements as accurate and consistent as possible. Another potential for technical error here would be if we happen to grab 20 freshmen at Emory, for example, and then 20 seniors at Georgia Tech, right? Freshmen versus seniors might make a difference in their overall heights. So you want to make sure that you normalize or control for that. Ensure that you're measuring only seniors at both schools, for example. Similarly, if we take male and female student measurements, we would want to make sure that we have a random sampling of males and females, or that we take a certain proportion of our measurements on males and a certain proportion on females, as we know that men are on average taller than women. All right, so let's say we do this, we collect our data. Here it is, but nobody wants to look at this graph. It's complicated, it's not easy for me to quickly look at it and get a sense for whether Emory students are generally taller or shorter than Georgia Tech students. So when you have lots of replicate data, you don't just throw it all up into your graph. You usually want to analyze that data a little bit first. Quite often you would take your average of your data. So here instead we've graphed the average height of all of our Emory students and the average height of all of our Georgia Tech students. This is a much clearer graph for us to look at and try to interpret. And from this graph we can see that our average height for Emory students is a little shorter than that for Georgia Tech students. However, we've lost all sense of the variation in this data. For example, what if of our 20 Emory students, everybody measured exactly 68 inches tall, right? That would be a very different scenario than if we measured Emory students and they had, very wide range of heights, with the average being 68. So whenever you simplify your replicates in your graphs, you also want to maintain a sense for how noisy the original starting data was before the simplification. So you generally do that by including what's called error bars on your graph. Here we can see our error bars for the Emory and the Georgia Tech students. And these error bars are just plus or minus the standard deviation. So that will give us a sense for the deviation of our individual measurements. So in this example, if I were to take more Emory students after this experiment, I would expect about 68.2% of those students to fall within this height range, okay, within plus minus 1 standard deviation. So this is really giving you a sense for the variation or the distribution of heights in your population. But what if we're more interested in how accurate our average is? Regardless of the variation in the population, we want to know how close is our estimated average Emory student height to the actual average Emory student height for the entire population. So you'll often see error bars that represent plus minus the standard error of the mean, and that is basically the standard deviation for your samples divided by the square root of your sample size. So as you increase your sample size, you take more and more samples, you're going to get a better estimate of the mean. Your standard error of the mean will decrease, right? So if I only measure 20 Emory students, I'll have a certain standard error of the mean. If I then go and measure 200, well, my estimate of that average height is more likely to be closer to the true population mean of all Emory students than my smaller sample of 20 students alone. Okay, so this is another thing that you'll see, and these error bars show you how confident you are in how close you believe your average is to the actual true average of the population. You'll also see error bars represented as confidence intervals, and these are related to the standard error of the mean, and they just represent the range where we are, say, 95% confidence that the true mean falls somewhere within this range. Okay, so when you look at this, do you think that Emory students and Georgia Tech students are statistically significant in their average height? Well, given how much these error bars overlap, I would say no, we haven't shown a statistical difference between Emory and Georgia Tech student heights because, right, there's still a large chance that the true population average would actually be the same between these two populations because these error bars overlap so much. Okay, so that's what I wanted to cover today. To summarize, right, it's important to really consider all the possible sources of error when you're doing experiments, to be careful in how you design your experiments to try to minimize these errors, and also it's quite important as you analyze your data and represent it graphically that you maintain for the people viewing your graphs a sense for the original noise in the data.